We're doing problems from chapter 13. Okay. So the first problem says, on a planet whose radius is, the radius is 12 times 10 to the 6 meters. The radius of Earth is 6.4 times 10 to the 6 meters. Okay, so this is almost twice the Earth radius. The acceleration due to gravity is 18 meters per second squared. What is the mass of the planet? Okay, so let me remind you, on a planet, I don't know what's going on. On a planet, when you're on the surface, mg is equal to the gravitational force, mass of the planet, times m divided by radius squared. All right, so g is given by that. So the acceleration due to gravity on the surface of the planet is g times the mass of the planet times the radius divided by the radius squared. All right, so in this problem, you want to find the mass of the planet. So the mass of the planet is g times r squared divided by the universal gravitational constant. Okay, so in the problem, they give you g, that's that. They give you the radius, and we know this constant. Okay? So you can calculate the mass of the planet. So the mass of the planet is, g is 18 meters per second square. The radius is 1.2 into 10 to the 7 meters square. And g, the gravitational constant, is 6.67 times 10 to the minus 11. And here's how you remember the units. See, in this formula, what is this? This is a force, that is Newton. So Newton kg square meter square. So Newton meter square divided by. Okay, so that's, yep. Well, mg is the force on you, and that force is the gravitational force. So that's the force on you. The force on you is your mass times your acceleration, and that's equal to the force of gravity. Okay. All right, so in this problem, so now we have to simplify this, and what I like to do is take care of the powers of 10. So this is 10 to the 14 plus 11, that's 10 to the 25. Okay, so, and this is a mass, so it'll work out in kilograms. Okay, so, and 18 times 1.2 square divided by 6.67. All right, so I will write this as 38.9 into 10 to the 24 kg. That's the mass of the planet. And the reason I write that is mass of Earth, you can check, is about 6 times 10 to the 24 kgs. Okay. So this planet is about, this planet is about 6 times Earth mass. let me look up the mass of the Earth, by the way. Yeah, so mass of Earth is 6 times 10 to the 24 kgs. Okay, so you can see that this is about 6.5 times Earth masses, this planet. Okay, yep. I can't hear you.
Is that Newton's law of gravitation equals to the energy in the stuff in this on the right? That would be Newton's law of gravitation, is it?
Yeah, this is Newton's law of
Oh, it
gravity.
is?
Yeah.
Okay, I see.
Yeah. All right. Again, this problem says the acceleration due to gravity on the surface of a planet is 3 times as large as on the surface of Earth. Okay, so you already saw that the acceleration due to gravity on the surface of a planet is given by that formula. Yeah. So the acceleration due to gravity is given by g times the mass of the planet, and now I'll write r as that's the radius of the planet. Okay, so I just switched it to capital R. Okay. The mass density of the planet is known to be twice that the Earth density. Okay, so if the density of on Earth is 5 grams per cc, on this planet it's 10 grams per cc. Okay, so it's heavier metals and stuff like that. So it's a metallic planet. What is the radius of this planet in terms of the Earth's radius? Okay, so the density on the planet is twice the density on Earth. The mass density, so mass density is twice that on Earth. The acceleration due to gravity on the surface is 3 times. Okay, so g on the planet is 3 times g on Earth. And what is it that they want us to find? What is the radius of this planet in terms of Earth radius? So they want us to find the radius of the planet divided by radius of the Earth. They want us to find what is this number. Okay. All right, so let's start substituting everything. So g on the planet is equal to g mass of the planet divided by radius of the planet square. G on Earth is g mass of Earth divided by radius of Earth squared. Okay, so they gave us these two facts. They gave us two equations because we don't know two things. We don't know the mass of the planet and the radius of the planet. That's why they had to give us those two things. Okay. So g planet divided by g Earth. I'm going to take this and divide by this. Okay. This is 3. The acceleration due to gravity on the planet is 3 times the acceleration due to Earth, on Earth. This cancels, so what we get is mass of the planet divided by mass of Earth times the radius of the Earth times radius of the planet squared equal to 3. Okay, so what we have done is this information, this piece of information has given that equation. And now let's use this piece of information. The density, okay, so the density of the planet divided by the density on Earth is 2, which is 4 pi by 3. The density is mass of the planet divided by the volume of the planet, the volume of a sphere is 4 pi r cubed. Mass of Earth all right. So you can see that this stuff cancels. So mass of Earth divided by mass of planet. So this is equal to mass of planet divided by mass of Earth times RE over RP cubed equal to 2. All right, so what we have done is the following. Again, see this equation, the fact that on the planet the acceleration due to gravity is thrice that on Earth gave us this information, gave us this equation, and this density equation gave us that equation. All right, what I'm going to do is I'm going to copy this. And bring it here. All right, so between these two equations, we should be able to solve this stuff. Okay, what is it that we want? We want this ratio. Okay. So what we'll do is we want this ratio. So what we'll do is we'll solve for this in terms of that, and then put that in here. Okay, so this equation tells us MP by ME equal to 2 times RP by RE cubed. Okay. RP by RE cubed. And now we'll substitute that in here. So we'll do that. So this is 2 times RP by RE cubed times RE by RP squared equal to 3. Two of those cancel, so what you get is RP over RE. RP over RE is 3/2. And that's what you wanted to find. So the radius of this planet is 1.5 times the radius of the Earth. Okay? The radius of the Earth is 4,000 miles, so the radius of this planet is 6,000 miles. In kilometers, the radius of the Earth is 6,400 kilometers, and so the radius of this planet is 9,600 kilometers. Okay. They ask you, what is the escape speed of a satellite located at the moon's orbit about Earth? Okay. Assume the moon is not nearby. So here's the Earth, and there's the moon. So if you had a satellite there, they want you to find the escape speed at this radius. Okay. Okay, let's okay, so the orbital velocity of Okay, so the moon's orbital velocity is 1 kilometer a second. Okay, so let's go back to our problem. So the moon's orbital velocity is 1 kilometer a second. Is the moon in a bound orbit? Yes, it's going around the Earth. Okay, so if you want to find the escape velocity, now you know that the escape velocity has to be greater than 1 kilometer a second. Okay. All right. So what is the formula for the escape velocity? Let's so here's the formula for the escape velocity. 2gm is the mass of the object you're trying to escape from, and r is the distance you're trying to escape from. Okay. So escape velocity is square root of 2gm divided by r. Okay. R is the distance you're trying to escape from. All right, so we just saw the mass of the Earth. What we know the mass of the Earth, we know this constant. What is R? R is the Earth-Moon distance. So we need to find the distance to the Moon. Okay, so distance to the Moon in kilometers is 384,400 kilometers. Okay, so R is, and we'll convert this to meters. So that's 5 plus 3, 8. Okay. All right, so now we can calculate the escape velocity. 2 times 6.67 into 10 to the minus 11. Mass of the Earth is 6 times 10 to the 24 kgs, and divided by 3.84 into 10 to the power 8 meters, and so the speed will work out in meters per second. Okay. So the escape velocity is, okay, let's take care of powers of 10. That's 10 to the 24. 24 minus 8 is 16. 16 minus 11 is 5. And what we'll do is we'll make this 0.2 and make that 6. Square root of 6 is 3. So this is 10 to the 3 meters per second. And what is left is 0.2 times 6.67 divided by 3.84 and times 6. All right, hopefully I did everything right there. Okay, what is it that we're expecting for the escape velocity? To be greater than what? 1. Yep, so that number better be greater than 1. Okay. So okay. So at least we passed one test. Okay. So if you want the moon to escape from your gravity, you increase its speed from 1 kilometer a second to 1.44 kilometers.
What does the G and M stand for the velocity escape, or the escape velocity?
G is the universal gravitational constant, which is that guy. M is the object you're trying to escape from. Yeah. Okay, this problem says an average sized asteroid located 5 times 10 to the 7 kilometers from Earth with a mass of 2 times 10 to the 13 kgs. Okay. So this is 2 trillion kgs, and again, a small car weighs about 1,000 kgs, so this would be 20 billion cars. That's the mass of this asteroid. Is detected headed directly towards Earth with a speed of 2 kilometers per second. What is its speed just before it hits our atmosphere? Okay, so when it's that far away, our initial, our final. Okay, so that's V initial, V final. Okay, so essentially what is happening is, what we'll do is mechanical energy is conserved. Okay, so these asteroids don't have rockets. As they fall closer to the Earth, they're going faster. Okay, and when this collides with the Earth, so you heard the dinosaurs went extinct 60 million years ago. It's believed that one of these big asteroids hit Earth. That collision threw up a whole bunch of dust, which encircled the whole Earth, and it was dark for a few years. And that's supposedly what killed off a whole bunch of stuff. Okay. So we'll calculate the energy of this asteroid. Okay. So again, like I said, energy, mechanical energy is conserved. So this is the mass of the asteroid. Okay, so this is its kinetic energy. And what is the formula for the gravitational potential energy? I'm sorry? Okay, so you could use that mgy. When do you use this? When you're within, let's say, 100 miles of the surface of the Earth. You are very far away. You guys remember the... Very good. Over R. Okay. So this is gravitational constant. This is the mass of the Earth. This is the mass of the asteroid. Okay. And that should equal... That should equal 1/2 mv final square minus gmm. And now what is the final radius? The final radius is essentially the radius of the Earth. Okay. So that's what we're going to use, the radius of the Earth. And now you will see that in problems like this, you'll see that it's a pain to use these formula for potential energy. mgy would be so much easier, but it doesn't work here. So, okay. So, what does that mean? Yeah, so the mass of the asteroid doesn't matter. If you threw a tennis ball with that speed, that's the speed with which the tennis ball would hit Earth. Okay? So we are trying to find the final velocity. So the final velocity is, and so we'll multiply by 2. So you can see that the final velocity, I'm going to do it in one step. Final velocity square is initial velocity square plus gm all right, so this times 2. Okay, I multiplied the whole thing by 2, so you get 2 and 2 here. I bring this over here, that becomes positive. Gm is common, which I pulled out, 2 times gm, and 1 over radius of the Earth, and 1 over initial radius. Okay, so that's the final velocity square. Okay, the initial velocity was 2 kilometers a second. We'll put that in SI units. Okay, so final velocity is square root of this. Initial velocity is 2 times 10 to the 3 square plus 2 times 6.67 into 10 to the minus 11. Mass of the Earth is actually, let me do, I don't want to make a mess here. Let me do one thing at a time. Let's calculate this term first. Okay. So let's calculate just that term. 2 gm 1 over re minus 1 over r initial. So 6.67 into 10 to the minus 11. Mass of the Earth is 10 to the 24 times radius of the Earth in 6.4 into 10 to the 6, okay, minus 1 over 5 oh, that's kilometers. All right, so now let me show you a little trick. Okay, so this is a number. This is 10 to the power of 6. This is, and you see this is, the 5 is approximately equal to 6. Because these two numbers are the same. This is 10 to the power of 10. This is 10 to the power of 6. So this number is 10,000 times smaller than this number. Right? It is like 1 minus 1 to the power of 10 to the 4. Okay? So we'll throw this number away. Okay? Did you guys understand that? So that's a little trick. You can put that in and put it in your calculator. It'll just make a mess and it won't make a whole lot of difference. Okay? So this is approximately equal to 2 times 6.67 times 10 to the minus 11 times 6 times 10 to the 24 times 1 over 6.4 into 10 to the power 6. Okay. All right, let's take care of powers of 10. Okay, so this is 10 to the 24. 24 minus 6 is 18. 18 minus 11 is 7. So And what will be the units? So this will have units of, what are the units of this guy? Just look at the equation and you should be able to. Huh?
Meters squared over seconds squared.
Very good. So this guy has to have the same units as this guy. Velocity as units of meters per second. Velocity square would be meters square per second over second square. Yep. So meter square over second square. All right. So V final square equal to V initial square. V initial square was 2 into 10 to the 3 meters per second square plus 2 into 6.7 divided by 6.4 into 10 to the 7. All right, so the final velocity square, you see, that's the initial velocity square, and this is how much it's sped up. I mean, that's the square of the, so most of the energy is from the potential energy being converted to kinetic energy. Okay, so, and 21 plus 4 is 25, square root of that would be 5. So V final is 5 into 10 to the power of 3 meters per second. Okay, assuming I did everything right. Did I miss out anything? This seems a little low.
On this page,
2.1 times 10 to the 7. Yeah.
on the first page below that, is the already doing the moving the RI over, should that be negative one, and the RI be positive one?
This comes over here, that'll become positive, and that's negative. So this is correct. Okay, let's see. What was the radius of the Earth? Oh, yeah, okay. Never mind. That's fine. See, Earth moon distance is that, and the escape velocity from here, see, that's greater than this distance. That's almost 10 times that distance. And the escape velocity from here was 1.44 meters, 1.44 kilometers a second. And this thing is coming essentially at 2 kilometers a second. So maybe it is correct. Okay, again, you guys go home and check. Okay. So what is it that we're asking for? What is the speed just before it hits the atmosphere? Okay. All right. So that's the speed just before it hits the atmosphere. Okay. 5 kilometers a second. Now they ask you, what will be the kinetic energy of the asteroid in the previous problem just before it hits Earth? Okay. So kinetic energy will be kinetic energy of the asteroid is 1/2 mv square. 1/2. The mass of the asteroid is here's the mass. So those 2 times 10 to the 3 kgs. And the velocity is 5 times 10 to the 3 meters per second square, and energy works out in joules. Okay, so this is 6 and 3 9. That half kills that, so 25 times yeah. I don't know, these numbers don't make sense anyway. So this is how much energy they have. All right, so in part B, they're asking us to compare this energy to the output of the largest fission bomb, so the largest atom bomb. And this is the largest atom bomb. The energy is 21,000 terajoules. So part B, you want the kinetic energy of the asteroid divided by the energy of the bomb. It's 25 times 10 to the 9 joules. Energy of the bomb is 2.1, and tera is 10 to the 12. That's 10 to the 15 joules. This doesn't make sense. So we've done something wrong somewhere. Okay? And your job as a homework is to go figure that out. Yeah, I don't know where I went wrong. But I remember the answer being thousands of bombs. Okay, so the energy of the asteroid is thousands of the largest bombs. Okay. And that would make sense. You need, it's not easy to wipe out all the dinosaurs just like that. Okay, so I don't know what's going on.
I see what you mean wrong there, but 2 times 10 to the 3 is supposed to be 13.
There you go. Good catch. Okay, so 6, that's 19. Now there you go. So now we're in business. So that's why you want to think about the answer. That's how you catch mistakes. So I'm glad I made the mistake, so we learned something. So 25 divided by 2.1. Okay, this makes a lot more sense. 120,000 bombs. That's good enough to wipe out the dinosaurs. Okay. So that's probably, I don't know if the entire world's arsenal is anywhere close to that, but so if we exploded all the atom bombs at the same time, we could. All right. Anyway, so here this problem says astronomical observations of our Milky Way galaxy indicate that it has a mass of 8 times 10 to the 11th solar masses. So 800 billion solar masses. So our Milky Way has 800 billion solar masses. The mass of our galaxy is that's a solar mass, and that's okay. And I don't know the numbers, but there are something like about 500 billion stars. So either there are quite a few massive stars, or so actually it turns out that the dark mass to normal matter is 5-to-1 ratio. So okay. A star orbiting on the galaxy's periphery is about 6 light years, 6 times 10 to the 4 light years away from the center. So the radius of r equal to 6 times 10 to the 4 light years. And so this star is going in a radius. What should the orbital period of the star be? Okay, so let me show you what this problem is about. And this was noted back in the 1930s. So this will take me a second, but okay. So here's a formula. This is the orbital speed of a satellite. The orbital speed of a satellite is gm, mass, m is the mass of this central object, divided by r squared. Okay. Now, this would be the speed of this guy, whether this mass was a point mass, or whether it was like this, or if this mass was spread over like that. This speed is influenced only by this mass, as long as the mass is symmetric. If there was any mass over here, remember what did Mr. Newton tell you, that if you're inside a shell, the gravity of that shell is 0 on you. Okay, so this guy's speed only depends on this mass. Okay, and this mass can be in any form as long as you have radial symmetry. It can be a black hole, it could be this, or it could be all the smeared out mass. Okay, and once you're outside this mass, you see the further out you are, your speed decreases as 1 over r. Okay, so your speed as a function of r should look like this. Your orbital speed 1 over square root of r decreases like that. The function looks like that. Okay, so once you're outside all the mass that you can see. So this is something somebody noticed in 1930s. Okay. Okay, so this is the famous graph. I believe it was somebody by the name of Mr. Zwicky. Okay, so here's the Milky Way. We did this for the Milky Way, and so this graph was put over a long time. Okay, so here we are measuring the orbital period of all these stars, or orbital speed of all these stars. Okay, you guys can see all the masses here. This is all dark. So in this region, the orbital speed should fall off as 1 over square root of r. And look at that, the orbital speed is constant. It's not falling off at all. We have a problem. Okay. So how could you solve that problem? So you can see that this is not falling off. That must mean there's mass over here. That was the first indication of dark matter. Okay, so very famous graph. Okay. So evidence for dark matter can be seen from the orbital speed of stars as a function of distance from the center of the galaxy. So this problem is related to that. Okay. Okay, so astronomical observations of our Milky Way galaxy indicate that is the mass. A star orbiting at this radius, what should the orbital speed of this star be? Okay, so we'll calculate the orbital speed of this star. So we know the mass, and let's calculate the orbital speed. So again, we can apply this formula again. So the orbital speed is gm by r. Okay. Is it 2 gm by? Shouldn't it be 2? Oh, yeah, okay, never mind. All right, so in this problem, we'll calculate that's what this should be. This is the mass, that's the mass. G is the gravitational constant, and this is the radius. Okay. What is a light year? Distance light travels in a year. Okay, and we'll get that. So light year, 1 light year is that many kilometers. So it's 9.46 into 10 to the 15 meters. Okay. Okay. All right. And anybody remember the mass of the sun? Okay, so that's another homework. You can't forget the mass of the sun for the rest of your lives. Okay. So let's calculate what should be the orbital period of the star. The orbital period of the Okay, so the orbital period of the star is 2 pi r divided by v, which is it's going in a circular orbit, and r, and v is gm by 1 plus a half is 3 halves. Okay, so the further out you are, the greater your orbital period. Okay. Okay, and what units will this come out in, the period? What are the SI units? In seconds. It'll come out in seconds. Okay. So the radius is light years, 6 times 10 to the 4 light years, 6 times 10 to the 4 light years, and each light year is 94746 into 10 to the 15 meters to the power 3 halves. G is 6.67 into 10 to the minus 11. And the mass in that galaxy is 800 billion solar masses. So all this mass is 800 billion solar masses. (800) into 10 to the 9, and each solar mass is this much. Okay. So this is what the orbital period should be. Okay. So let's take care of powers of 10. Okay, again, this is 39, 41. 41 minus 11 is 30. Square root of that is 15. So 10 to the 15. And you have 15 to the power 3 halves, so that gives you 15 to the power a half. We'll make that, okay, so 15 to the power a half is 7.5, plus 4 is 11.5, and so that'll be 10 to the power 11 times root 10, 6 times 9.46 to the power 3 halves. Oh, no, I made a mistake. All right, so that's 10 to the 30. Okay, that part was correct. Oh no, shoot, I made a mistake. Okay, 30, 32. Yeah, that was fine. 32, 41 minus 11, 30. That's 15. 10 to the 15, and this is 10 to the 19. Well, I'll make it 10 to the 18. I'll do it 60. 10 to the 18 to the power 3 halves. 18 to the power 3 halves is square root 18 to the power half is 9. 9 times 3 is 27. So you have 10 to the 27 there and 10 to the 15 down here. 10 to the 12. Did I do that right? And that's in seconds. So 2 pi 6 times 9.46 to the power of 3 halves, square root of 6.67 into 16. We'll know in a second if I did it right. Okay. Okay, so the period is 260 into 10 to the 12 seconds. And okay, each year has 365 days. Each day has 24 hours. And each hour has 3,600 seconds. Okay. So that's the conversion to years. $8.24 million years. That's what it works out to. And I think I did something wrong. Okay. So what should be the orbital period of the star? So if its period is 6 times 10 to the 7 years instead, what is the mass of the galaxy? Okay, so this is the matter we can see. Okay. So we got this many years for the calculated value of the period. The actual period is 60 million years. And how is the period related? Okay. Okay, so okay, the period is greater than the mass. So we did something wrong here. Maybe your calculated period needs to be greater. Yep.
Make the 6 a 60 when we do exponents and relations for that last, or the last t equals on slide 4. For the, shape.
Which one?
By the 2 pi on the last t,
Mhm.
that 60 is 60, the exponents, below that number.
This one?
No, the next t equals, and you make that 6 a 60 in the top. For the exponents.
Here?
Yeah, you made that 6 to the 4, so you make that a 60.
That should be a 60.
Yeah, for the exponent calculation.
No, it's 6 light years.
When you were doing the calculation for the exponents, so you make that 60.
All right, let me do this again. Yeah, so this should be bigger. This number should be bigger, essentially. Okay. So 15, 19. Oh, I see what you mean. Oh, yeah, I borrowed one. Yeah, very good, very good. Good catch. So that should be 60. Yep. And so this should work out too. Oh, that will fix it. Thank you. Um, There you go. That will fix it. So this is instead of that, that's 8,225. There you go, 260 million years. Okay, so that's calculated. This is the actual observed period. And look at the formula for the period. T is 2 pi r. There you go. So T is 2 pi r to the power 3/2 square root of gm. Okay, so the observed period is 60 million years. From all the stars that we can see, it should be 260 million years. Okay, so if the observed period is smaller, there must be a lot more mass than we can see. That's evidence for dark matter. Okay? So this is the kind of calculations that go into, and imagine this, you can't just put this story overnight. Okay, we did a calculation and we made silly mistakes and stuff like that. So all these scientists, they're doing so many more calculations. And they're sweating bullets before they'll say anything about this kind of stuff. Okay. I mean, in as recently as so in 1998, okay, so since so these are all galaxies, and Mr. Hubble back in 1928, this is a good, back in 1920s, realized that all these galaxies are moving away from each other. Okay, so we are living on this galaxy, and every galaxy is moving away from us. That's because we have bad breath. Yeah. Now, if you think about this, there's nothing special about us. If you were on any other galaxies, you would observe the same. And what Mr. Hubble discovered was, if you are here, let's say this is moving at 100 miles a second. I'm just making up numbers. If this guy is twice as far, he's moving twice as fast. All right. Now, the only way this can happen is, so imagine a rubber sheet, and you paint galaxies, and if you stretch the rubber sheet, then this can happen. So these galaxies are not moving away. What is happening is this space between us is expanding. I mean, that must, when we realize that must, imagine the shock. All right, so space itself is expanding. That's what's happening. All right, now let's, you all are experts at Newton's law of gravity. Okay. What is happening to this as I throw it up, as it's rising up? I'm sorry?
Decelerate.
Decelerates. So this is a mass, this is a mass. There's no reason Newton's law should not apply. So what do you think should be happening to this guy? He's moving away from you. He should be decelerating. We've been certain of this since the 1920s. We even called it a deceleration parameter. And we've been, ever since, we've been looking at how the universe has been decelerating. I mean, we've been looking for a long time. In 1998, so two big groups realized instead of decelerating, the expansion is accelerating. So that's one of the biggest discoveries. It is accelerating. They sat on that thing for 2 years. Everybody is grabbing bricks, you know. There's no way we could be right. How can you make this accelerate? I'm sorry? No, once you've thrown it away, is there any way this thing could accelerate? If it had a rocket on it, some source of energy. Now you know where the dark energy came from. Okay, so we need a source of dark energy. All right, so you know, from just our little problems, we can figure out all the So now in that one problem, you see dark matter is 24%, normal matter is 5%, dark energy is 70%. You saw all of that in that one problem. Well, not quite, but you know, you got an inkling of that. So simple problems like that. And you see, I mean, on a simple problem, I made several mistakes. You just have to be a little more careful, that's all. All right. See, there's that number that we calculated, 260 million years. There, 260 million years. All right, one more problem, last problem, and we'll be done. Okay, this guy is tired. I mean, he's falling asleep. All right. So the sun orbits the Milky Way galaxy once every 260 million years with a roughly circular orbit averaging a radius of 3 million light years. Calculate the centripetal acceleration of the sun in its galactic orbit. Does your results support the contention that a nearly inertial frame of reference can be located on the sun? Calculate the average speed of the sun in the galactic orbit. It's not a very interesting problem. Do you want to do it or something else? Or do you want to see this? So, okay, so I'll tell you what the problem is asking for. So this is the Milky Way galaxy. Our sun is somewhere here. And nothing in the universe is stationary. Everything is moving. Okay, and so we are going in a circular orbit. Okay? And what this is saying is it takes us 260 million years to go around. Okay, when you're going in a circular orbit, are you accelerating? You're going at uniform speed. You are accelerating, you have a centripetal acceleration. And what this part of the problem will show you is the centripetal acceleration is very small. So you can essentially consider that as going at, as long as you're not doing an experiment that lasts 200 million years. So if you're doing anything that that a short time, then this is an inertial frame. It's going at constant velocity. Okay? That's what the first part of the problem is. Calculate the average speed of the sun in the galactic orbit. So you want to calculate the speed. Let's see if I remember it. Okay. Anybody know the speed of the Earth around the sun? So we're going at 30 kilometers a second. Okay. And this speed, I believe, is somewhere around 200 kilometers a second, something like that. So our sun's speed is around 200 kilometers a second. So the sun is carrying all the solar system, the entire solar system is moving at that speed. Okay. So if you did astronomy and all that, you'd know this kind of speed off the top of your head. Okay. So that's the problem. All right, we'll just do one more problem. And so this is using Kepler's third law. Io orbits Jupiter with an average radius of that many kilometers. So this is and a period of 1.77 days. How long does it take for the moon to go around the Earth? I'm sorry? 28 days, a month, okay? So this is going around Jupiter in 1.5 days. That's fast, okay? Based on this data, what is the mass of Jupiter? Okay, so the more massive the object, the faster you're going. Okay? And so here's we'll use Kepler's third law. Oh, well, actually, I don't want to use Kepler's third law. Okay. So here's Jupiter. Here's okay. Okay. What is providing the centripetal force? mv squared by r, or is gm mass of Jupiter. Okay. So mass of Jupiter is what we want. So mass of Jupiter is v square r divided by g. The period was 2 pi r divided by v. Okay, so okay, we'll substitute this in here. So mass of Jupiter is I guess we should have used we are essentially deriving Kepler's third law, but So this is 4 pi square r cubed divided by g t squared. Okay. So this is Kepler's third law says t squared over r cubed equal to r cubed is 4 pi square over gm. That's Kepler's third law. Okay. So we essentially derived it. Okay. But anyway, so there's the mass of Jupiter. We know the orbital radius of the moon. We know the period. So we'll put all of this information in. Okay. So 4 pi square. What is the orbital radius? 4,201 kilometers. 4.21 into 10 to 2 into 10 to the 5, 10 to the 8 meters cubed. G is 6.67 into 10 to the minus 11. Period is 1.769 days, 1.769. Each day has 24 hours, that many seconds, square. And so this will work out in kilograms. All right, I'll try not to make a mistake here. That's 10 to the 24 in the numerator. And you guys help me along. 10 to the 24. What is the mass of what is the Earth's mass? 6 times 10 to the 24, okay? And Jupiter's mass is, I don't know, maybe between 100 to 1,000 times more than that. So Jupiter's mass should come out to be somewhere in the 26, okay? 10 to the 26 or 10 to the 27. Okay, that's 24. I'll make this 3.6. So 3, 4. 4 square is 8. 8 minus 11 is minus 3. And 24 plus 3 is 27. Okay, so we are in the right ballpark. Okay. 4 pi square times 4.22 into 4.22 cubed divided by 6.67 times 1.769 into 2.4 into 3.6 squared. Yes, so that's what I have. Hopefully it's correct, but that should be easy to check. While I do this, somebody check the mass of Jupiter online. About 300 Earth masses. Huh?
Online it says 317 requests.
Okay. All right, 1 out of 10. I got it right. All right, guys.